Okay, let's get started. So welcome everyone to the fourth talk in our summer Chilloquium, co-organized by Harvard and MIT Society of Physics students. I'm Jennifer Song, and I'm an undergraduate studying physics here at Harvard, and I'm one of the organizers of our Chilloquium speaker series. I'm here today with my co-moderators, Tung, Minchul, and Chan, and we're very honored to have Dr. Anjali Tripathi from NASA Jet Propulsion Laboratory to speak with us today. If you have any questions at any time, you can raise your hand in the Zoom participant sidebar and we will call on you, or you can privately send a message to me and I'll ask for you. We will prioritize those who can raise their hands in order to make our event feel as conversational as we can. And in the spirit of keeping this a more relaxed and personal conversation, we also have a request that everyone be muted unless they are speaking, and also have their video on if you're willing and able. Now, before starting the talk, let us briefly introduce today's speaker to you. Tung?
Thanks, Jennifer. We are extremely excited to have Dr. Anjali Tripathi give a talk with us today. Dr. Tripathi is an astrophysicist and the science ambassador of NASA Exoplanet Exploration Program. As the program's lead science communicator, she works to make science accessible for all. Affiliated in Harvard-Smithsonian Center for Astrophysics, her research has explored on how exoplanets form and lose their atmospheres. Connecting science to society, she previously led science and climate policy at the White House, where she was appointed a White House Fellow. She earned her Ph.D. and Master of Arts in Astrophysics from Harvard, Master of Philosophy in Astronomy from the University of Cambridge as a Marshall Scholar, and Bachelor of Science degree in Physics from MIT. Thank you very much, Dr. Tripathi, for giving a talk at Chilloquium this week.
It's my pleasure. I'm going to go ahead and share my screen in just a second, and then we'll get started. So just before I lose seeing all of your faces, can I just get a show of hands of who is an undergraduate right now? Okay, I see. You can all see virtual hands. Okay, about half. And then who's a graduate student? Any graduate students? Okay. Great. So this helps me to put myself in your shoes a little bit because I think it's always really important to know who your audience is before you talk to them. Okay, so let's see. Is this going to share my screen? Okay. So as was already mentioned, I work out in Los Angeles at NASA's Jet Propulsion Laboratory. I have a secondary affiliation at the CFA, the Harvard-Smithsonian Center for Astrophysics. And I actually just wanted to tell you a little bit about my journey to where I am now, because what I do now that counts as being a physicist is not at all what I expected it would be when I was an undergraduate. And it's sort of surprising that I can do that. And so I thought I would reflect on that experience. And thinking about reflections and selfies, I wanted to start with this great picture of the Perseverance rover selfieing with the Ingenuity rover, where it's taken its robotic arm and actually taken a picture of both of them on the surface recently. And Mars rovers are basically the hallmark of what comes out of JPL where I work. So if you need that connection, that's what it is. Although I confess, I do not work on rovers. Also talking to all of you is kind of exciting because I was president of the MIT Society of Physics students back in the day. All of the content on the website, shockingly, is still what I wrote. I don't want to say almost 20 years ago. So all of this, should I be a physics major, or course 8 as we call it, was something I wrote. On the right is a picture of the Chilloquium dinner from when the physics students hosted Kip Thorne out in Kendall Square. So lots of fond memories. And we'll come back to sort of what I wrote here in a little bit. But like I said, what I am as a physicist and a scientist is not what I expected. And there's this experiment. It turns out lots of outreach has its own research studies papers. And so Fermilab did this experiment where they would ask students to draw a scientist before someone came and did outreach and after. So these are two different students. These were, I think, second graders. And on the left, they drew what a scientist was before I came to talk to them. And on the right, it's what a scientist looks like afterwards. And you can see on the left, there's some lab coats and beakers. You might know in physics, there is biophysics, but for the most part, there's not a lot of lab coats and beakers. And on the right, there are some more computers, there's some more gender diversity, there's all of that. And so I just start with this because you never really know what else is there until you see it. And I'm hoping my talk today will give you an idea of what else being a physicist can look like, as well as just to say the image on the top right corner is from when I was a judge at the Tribeca Film Festival, which is a cool thing to do because the Sloan Foundation, which in addition to doing things like the Sloan Digital Sky Survey, also funds film schools across the country to help them portray science better on screen. So The Martian, Hidden Figures, all of these have received grants that have helped that process along. And so I, as a scientist, was a judge. And Picture a Scientist is the name of a film that talks about gender disparities in science. It features MIT, amongst others. And I highly recommend you all go watch that documentary if you haven't already. So that's a movie plug. And as was said before, feel free to interrupt with questions at any time. So, you know, I work at NASA. I'm an astronomer. That's not particularly surprising. People are always, I think, quite worried about finding the next right thing in research projects. So I thought I would share with you some of the places I had research experiences in college and grad school. So I was a UROP, so a research student at MIT in a couple of different labs, both in geophysics and in astronomy. I spent a couple of summers in different places. One of them was at Fermilab doing particle physics and electrical engineering. Another was in galaxy and dark matter astronomy in Paris. And then I went off to a couple other places afterwards. But you might say, like, that's kind of a random mismatch of things. And I would say it all starts with when I was in high school. I came from Los Angeles before moving to the East Coast. And I was really into earthquakes because when I was a kid, we had the Northridge earthquake and I had to move out of my house for a year. And if any of you have experienced an earthquake, a really serious one, you'll see that on TV. And of course, this is back before everyone looked online, but on TV, when the news comes up about an earthquake, there's always a seismologist who will come and explain what happened. And to me, it was the coolest thing that a seismologist, right, a scientist, could help you make sense of the world around you and basically keep you safer by knowing about aftershocks and what had happened and where it had happened. So I actually came to college thinking I would study geophysics, and my first research experience was actually in seismology. And when I got there, I thought, this is not a great match with personalities and everything else. So I think I'll try something else. And I happened to get sophomore standing at MIT, which is where you can graduate a little earlier if you like. But they lost the paperwork. So I basically ended up having a week to declare my major. So whereas I wasn't sure if I wanted to be a math major or a computer science and electrical engineering or earth science, I went, okay, I'll just study physics. It's good for everything. Yeah, that's great. And on the right are pictures from my internship at JPL. So I was a high school intern there for a couple of summers before coming to MIT. So I had all of these things floating around. And this got a little bit out of order, so we'll come back to that in a second. But as it turns out, I said, okay, I'll study physics. And along the way, I discovered that actually I really like astrophysics of all of them. And so that's what I did for my undergraduate thesis. I happened to not be sure if I wanted to go to graduate school and get a PhD for 6 years, since that's such a long time. And so I ended up applying for scholarships to let me do a master's in the UK. Because in the US, it's kind of hard to get a master's in physics unless you drop out of your PhD program. It's not like a lot of engineering programs where you can get a terminal master's degree. But in the UK, that's actually something you can do. And so I happened to apply for and be lucky enough to get the Marshall Scholarship, which is like the Rhodes Scholarship, but it lets you go anywhere you want. And I really wanted to go to Cambridge because that was where Newton and Cavendish and all of these folks were from. So I did a master's there and thought, it's okay, all right. So I'll continue. And so I came back to Boston and did my PhD at Harvard. So it means all of my degrees come from Cambridge, just one or the other side of the Atlantic. And so on the top, though, you can see that the way I thought this would work when I was an undergrad was you go to grad school, then you become a postdoc, and then you become a professor. If you're lucky, maybe you can skip the postdoc. Because I like doing research. It's something I'd done a lot. But the thing I discovered was, well, actually, I really like doing a lot of these other things. And I'm not sure I want to be a research faculty member. And so I ended up going to graduate school, many years of graduate school because of the master's. And then I actually went off to the White House towards the end of my PhD, and went into industry and came back to JPL. And along the way have been that research associate at the CFA. So just to pause for a second and say, this is a figure from a blog entry I wrote after graduating from college. Does anybody know what that figure is if you don't have the on which trajectory is my life and the different axes? Can anyone tell me? I feel like you should just unmute and say it or write it in the chat, whichever folks prefer. I feel like somebody knows what this is. Anybody? Okay.
I can go. It's like the evolution of the universe.
It's the evolution of the universe. So what should the y-axis be?
The scale factor.
Yeah, so this is basically, is the universe going to come back on itself? You're gonna have a big crunch. Are we gonna expand forever? What's going to happen? What trajectory are we on? And I can tell you that at the time, I did not feel like I was doing anything other than the orange one. I remember going to the academic advisor for physics at MIT and telling him, please tell me my grades are bad enough that I can't go to graduate school. And he told me, I can't tell you that. But I just figured I wasn't the top student in my class. And I had all of these feelings. And so I just put this up here because I don't think we talk a lot about failures in physics, especially at the student level. And Emma, thanks for the note that unmuting is not allowed as of now. So hopefully the SPS team will fix that. But yeah, we don't talk a lot about not being successful.
Oh, okay. so like regarding the unmuting, like, so I think, yeah, please like raise your hand and then we will like ask you to unmute like right away. So like, please do so. Yeah, whenever you have a question or something. Yeah.
Thanks for clarifying, Mitchell. So yeah, so I just wanted to put this up and we can talk about this now. We can talk about this at the end. When I gave a version of this talk at Caltech a few years ago, it sort of turned into group therapy, which I think was appreciated by everyone. So I'll just put that out there that I'm happy to have that conversation. But anyhow, so I did all these things. And so I went from being an intern at JPL to, you know, coming back here a few years ago. And along the way, a few other things happened, sort of involving planets. On the right is a picture of Halloween at the White House. John Kerry, who used to be the Secretary of State, made a joke about me when he heard about my studying hot Jupiters, which are exoplanets the size of Jupiter, but much closer in, about 100 times closer to their host star. And he thought it should be an oath like, by Jove, hot Jupiter. And so when I was invited to Halloween at the White House and I didn't have a costume, I cut out a pizza box and painted it and made myself a hot Jupiter. So my job today involves a few different facets. And so I thought I would just quickly talk a little bit about each of them. So I am NASA's first exoplanet exploration science ambassador. And that means that I do a range of mission design for future missions and figuring out what should we be doing for the future of exoplanet exploration. But it also means that I'm the lead science communicator for the program. I also work on climate at JPL. So I do research into sea level rise, and we'll talk a little bit about that. And given my background in DC, I work on policy and how we can connect different pieces together. So on the right is a picture from when Governor of California, Gavin Newsom, came to JPL last year. And I'm showing him actually a model of a satellite that's used to study sea level rise. Any questions before we go on? All right, away we go. So into exoplanets. So I happened to be looking at a textbook I had from freshman year yesterday, and in it said that there were about 90 exoplanets to date. You know, I'm not that old, and so I think it's kind of remarkable to think that since I was in college, we now know that there are thousands of exoplanets, right? All of these planets, sadly, were discovered after I graduated from college, but they're all, those dots show planets that were found around stars by the Kepler spacecraft. And so when we look at the, you know, plot of the number of planets discovered over time, and note that it's only plotting planets that we have known masses. So this isn't all 5,000 plus planets, but this is a subset. You can see that over time we've gotten down to smaller planets, right, and on closer orbits. But the thing about that is that most of them, and you can see this on the right, were discovered with the transit method. And so that's what the Kepler spacecraft used. It's what I had some observations with. And so just to take a moment to remind you what that is, if you're not familiar, the transit method looks for changes in brightness of host stars. So you have lots of missions that are just looking at the visible light from stars. And when the planets pass in front of them, what you see are these dips in light. And so if you actually plot that, what you'll see is this characteristic dip. Now, granted, there are lots of other astrophysical sources of dips, right? You could have a binary star system, you could have all kinds of things. So you have to have enough information to characterize it as a planet. And back when I was an undergrad, this was still pretty uncommon to see. So on the right was my first paper, a figure from that, and it was taking observations of this one exoplanet called WASP-3b, and actually looking for, you can see that there are some of these points that are sort of anomalous, right? And it used to be really exciting at the hopes of finding another planet overlaid on your transit signal. So something called a transit timing variation. We have found planets through transit timing variations. Like if I go back, you can see we have found 0.46% of all exoplanets. It's down here at the bottom through transit timing variation. So it's pretty uncommon. In my case, it turned out to be some clouds, and that's why you don't see it consistently. But transits, of course, have been used to find all kinds of exciting things. So one of them is this detection of a system called Trappist I, where it's got 7 exoplanets orbiting this M dwarf, so this little red star, about 40 light years away. And you can see all of the dips over this 20-day period that allow you to actually disentangle 7 planets in the system. And what actually makes it so interesting is that of these 7 planets, 3 of them are in what's known as the habitable zone around the star. So if you look at our solar system, right, and the sun in our solar system is both brighter and bigger than the red dwarf that makes up Trappist I. So our habitable zone, which is where water has the conditions to be liquid on the surface of the planet. So it means that you're not so close in that it's hot and steamy, not so far out that it's ice, as well as you have the right atmosphere and pressure to actually keep that water on the surface of the Earth. And there are all kinds of different definitions actually of habitable zone. So, you know, whether Mars and Venus count, it's open to debate on if you're making it a conservative definition of the habitable zone or not. So when someone tells you about habitable zone planets, there's all kinds of ambiguity, but the general idea is liquid water on the surface for a long time. So of course, around a smaller star, you would move this closer in. And so that's why you see this whole system would fit in much closer to the star than the orbit of Mercury to the sun. And you can see that these 3 planets are not only in the habitable zone, but it turns out they're actually pretty similar to Earth size. And so because you have these small planets in the habitable zone, and it's a small star nearby, it means that we can make lots of follow-up observations. And so people are really excited to see what the James Webb Space Telescope is going to find for all of these planets. There were already observations of some of them. There was a paper in Nature that came out a couple of weeks ago that said, nothing here, but that was one of these inner ones. So what we're really interested in are these 3 and understanding what's in the atmosphere, which we can actually characterize. So where I work in the Exoplanet Exploration Program Office, we generate a lot of art, right? It helps us communicate to the public what's going on and to each other. And so this is art on the left of what it would look like if you were on Trappist 1E. So you can see if you were in here. And it's interesting to actually work with the science team. My meetings this morning were with the designers on how we can make a new set of posters because it all starts from a scientifically accurate place, which is, I think, a little bit different from how some art normally works. And on the right, you can see some Valentines we released a few years ago about You Had Me at Habitable. So again, there are all kinds of different exoplanets. And I showed you that image earlier with the different colored dots. And each color corresponded to a different sized planet. So in exoplanet land, we found all kinds of planets that we don't see in the solar system. There are things that are bigger than Earth, smaller than Neptune that we just don't have. And it turns out if you actually make a census of the exoplanets known to date, you can see that there's actually this bimodal distribution. We tend to find a lot of planets that are around super Earth sized and some that are mini Neptune sized, but there is this valley in between. And the question is, why is that there? Is this something where we just need more observations and it will disappear? Or is this a genuine physical process at work? So one of the questions I wanted to tell you about, because basically all of my research and thinking is about what else is out there. Like, it's great that we found these planets, but could we find something out here? Could we find something out here? Could we find something in here? And so part of this is making use of transits, but looking in a different wavelength. So it turns out if you look in ultraviolet light, the planet will actually look bigger if you have gas in an extended atmosphere around the planet. And so it turns out that there are two systems on the right shown that were observed with the Hubble Space Telescope. And you can see these transits. Now, granted, it's a spectrum, but don't worry about that. In terms of the x-axis is in velocity, but you can just think of it as being in time effectively. And you can see that there is more absorption during transit. And that's because you have this bigger atmosphere coming and blocking some of that light from the star. So what you're actually seeing is evidence that you have gas coming off of the exoplanet, and it's reaching to such extents that you can actually say it's unbound from the planet and is streaming off into space. So this is something that was studied for a while, well before we knew about exoplanets, because people looked at the solar system and said, why are Mercury, Venus, Earth and Mars rocky, and then everything outside of that is just big and gaseous? And so the question was, and if there's a question, feel free. I can pause and take the question.
Oh, sorry. I think I have a clarification question.
Yeah.
So yeah, you said both of the figures at the right are do correspond to the the actual data that we got from the telescope, and how is the difference between the two figures in the case? Are they? Yeah.
Yeah. So what you and I misspoke a little bit when I said you should think about it as time. I was just saying that when you look at what's on the right, you have the comparison of the amount of light that you're receiving from the system, both when the planet is out of transit, so it's not in front of the star, and when it's in transit for the top one. So the thin line is before transit, and during transit, you can see it's deeper. And that's because you have more blocked by the planet. Because if you didn't have this extended atmosphere, right, if all of the atmosphere was just the size of your ball of rock, then it should be not absorbing ultraviolet light. So the fact that you're seeing something is evidence that there's gas that's in between you. On the bottom, it's actually a more interesting result because you can see it says pre-transit and post-egress. So this is when the planet is actually over here, but it's because it has a tail of gas going behind it that's still blocking some of what you see. Does that clarify what's going on? Okay.
Oh yeah, thank you so much.
And so as I was mentioning, part of why people used to study this is they wondered if everything in the solar system started out like Jupiter and it gradually lost its atmosphere by being close to.
Also, I think there's another question on the chat. Why are there peaks on each side of the transit?
So you should note that on the right, those are just the spectral lines of what they look like, right? So these are just whatever chemical molecule is in the atmosphere and of the star and planet. On these are both Lyman alpha. So what you actually are seeing in the middle that's marked geo is also there's the emission from the Earth that's getting in the way of the Hubble Space Telescope. So you don't tend to trust anything in this dashed region. But what's on the outside is just what the stellar spectrum looks like. So it's nothing to do with the transit. That's separate about the physics. So anyhow, people were curious if you lost all the atmospheres. It turns out in the solar system, for planets that size, you just wouldn't lose everything. But part of my PhD research was actually doing the first 3D models of this computationally. And it turns out to be kind of a hard problem because you have to both do the chemistry of what the species in the atmosphere are doing, moving the heat around. And so it's a hydrodynamical simulation. For these ones, it didn't have, if any of you are familiar with MHD, there was no magnetohydrodynamics in this. It was just smooth particle hydrodynamics. But you can see it had all kinds of fancy refinement to get you really detailed, to keep gas bound at the surface, and to understand what happens with it. And so on the right, I'm actually really proud that it made the figure in the reviews article for the year of understanding how atmospheric escape works for exoplanets. On the left is an artist's conception of this, because it turns out for hot Jupiters, so if you do start with something like Jupiter and you're 100 times closer to your star, you're going to have just huge amounts of mass loss, but it turns out not to be catastrophic for you. But if you're smaller, and we go back to the one a few slides ago here, right? It turns out if you start out at the right size, you can actually be obliterated away. And so the current understanding of why you have this gap, we call it the Fulton gap based on this paper, is because of atmospheric escape, and how even if it turns out that we find more planets, we still expect to see some depletion because it's such a significant factor. And again, this is just sort of a comparison of our own solar system of what else is there, and how atmospheric escape is really different. Because on Mars, it's been really significant. There have been multiple spacecraft that have studied this, one called MAVEN, the Mars Atmosphere Volatile Evolution spacecraft that is just trying to understand, if the gas is no longer there, where did it go? And you can actually see cool images of the extended atmosphere floating off into space around Mars. And I happened to be lucky enough to give a TED talk about all this when I was in grad school. But it was, for those of you at Harvard, you know about all of the tutors associated with your house. And so I was a non-resident tutor in Mather House. And we have high table dinners, and someone said, hey, you should come and talk about this. And at the time I thought, wow, there couldn't be anything more boring to tell people about. Nobody will care about atmospheric evolution. But now that people have found the planets in that distribution, because this is work like more than 10 years ago, it turns out to be really popular. So that's cool. Okay, so this is how it's going, how it started based on that meme, right? How it's going, how it started. Another question that I'm interested in, besides sort of what else is out there and where did it come from and how is it changing, is on what other planets could be forming that we haven't seen yet. And the way we study planet formation is based in part by our understanding of where planets form. So if you look at the sky and look at the ecliptic plane, you can see planets in a line. So up until 1781, we only knew about 5 planets beyond the Earth. And it turns out, not only are there more exoplanets, but we can actually learn that in our solar system, the planets are orbiting in this disk, right? And it's all in the same direction. It's all very flat. We call it the protoplanetary disk. But since the 1980s, we've actually found a lot more of these disks. So in the 90s, we used the Hubble Space Telescope to actually image. This is the Orion Nebula, and you can see at that time we called them Proclids, as short for protoplanetary disk. And they just look like shadows because it's dust. Because the way that you're forming a protoplanetary disk is when a star is forming, you have a lot of gas and dust coming together and collapsing, and it's spinning. And as it's spinning with that angular momentum contraction, it's going to form into this disk. And out of the 99% of the material that becomes a star, about 1% is left behind. And it's kind of interesting to zoom in and imagine what's happening in there that's going to form planets, because the planets that we end up with today, and they're huge, but we also have a lot of other material in the solar system. We've got asteroids and comets and moons and minor planets. And so all of this had to start from microscopic particles, basically the size of smoke, that had to get larger. And so part of that are collisions where some of it's stuck together. Of course, sometimes it can break and you can have other physics, but the idea is that you had to grow entire planets from these micron-sized particles, basically. And if you want to understand these micron-sized particles, it helps to be able to actually see where they are. So the image I showed you from Hubble was a visible image, but it turns out that this dust emits, you know, at about the same wavelength as the particle size. So in the same way that you have thermal emission that you can see on the left here from the kettle in IR, on the right, you can see what the disk around this young star, UZ Tau East, looks like. And so that's this disk, and that's made with radio observations. So in spite of being an astronomer, I am both a computational astronomer. The last thing I showed you, that one figure, is from a lot of work I did in computer modeling. And I have worked in observations at radio wavelengths, but it means that I basically know nothing about looking at the night sky, right? All of these beautiful telescopes are giving me images that look like blobs. But they allow us to actually see into the dust, right? So we can understand what's happening and see inside the disk rather than just seeing what's at the surface. So the back half of my PhD, because my first PhD advisor left Harvard conveniently during my degree, was to look at lots of disks and what we could learn about them. So it turns out if you want to measure the size of blobs, it's kind of hard to decide how big they are because you have to figure out what your extent is and you don't want it to be resolution dependent. So I came up with a new metric for size, and it turned out when I plotted everything, I said, oh, hey, it looks like there's this trend. And then papers after that and other ones that I helped with showed that, oh, hey, that trend sort of works. It turns out that the size of the disk, the radius, the luminosity, or how bright the disk is, goes as the square of the radius, which at some level you think, oh, that makes sense. A bigger thing should be brighter. But on the other hand, they're not all the same age, right? They're very different. And you can actually start to see this tail going up. And we do think that there's probably some evolution because the younger disks are up here on the upper right, and the older disks are sort of on the bottom left going up. And it's because as time is passing, things are dissipating and sort of expanding out a little bit. And so that's why you're getting this larger radius. But it was kind of neat to think about because on the left is a figure from Fred Whipple, who used to be the director of the Harvard College Observatory in like the 70s, where he said, well, if you look at the sun and you look at all the material in the disk around it, and you look at the pressure as a function of radius, if you assume that everything was monotonically decreasing, right? So it had highest pressure at the center, least outside, everything would just sort of stream in. Right, and that's what you see, this radial force on gas. But if you had this area of higher density, then you can actually see that the forces are leaving you with this little extrema, right? And so you see that the motion of the particle is things get trapped there. And so if we play with different models to explain why you see this trend, there are a couple of explanations that are good, but one of them that's kind of interesting is that it works if you add in structure in the disk. So you might say, well, this isn't great on the right. And I would say, yeah, it's just a proof that you can do it, not that that's definitely what explains it. But the reason this is interesting is twofold. So one of them is that since my work, we've used the ALMA telescope in Chile. So this is the world's biggest radio telescope array in the Atacama Desert, so sort of contiguously. And so this is work by my former group, showing all of this structure around disks that looks almost galactic, right? You see spiral, or you see rings, there's actually spirals, there's all kinds of structure. And it turns out that basically every disk you look at with ALMA at high enough resolution and sensitivity shows you that there's substructure. So that's interesting, but it's also interesting because it turns out our theoretical understanding of planet formation has been stuck on what's called the meter size barrier, that you can have planets that are forming from micron sized particles up to rocks. But once you get to about a meter, there's just this question mark of how do you keep growing? Because at that point, your mass is such that you should actually be moving inwards and you're swept inwards before you can grow faster. But we know that we have big planets. So how do you actually get there? So that's what some of my work was thinking about, was how do we deal with this? But I will say it is still an unsolved question. We know that there must be some way to get over it. I don't have an answer for you today. If I did have an answer, that would be very cool, but unfortunately I don't. But just to say that I think we talk a lot about planets in terms of the search for life. And since coming to NASA, it's been a little bit of a shift for me because I've always been really interested in the physics of what's going on and is consistent across different systems. To me, a single planet hasn't been as exciting as the underlying physics. But every 10 years, the astronomical community comes together and puts their recommendations forward of what we should be focusing on for the next decade. So in 2020, it was supposed to come out. It came out a little later because of COVID. This report actually recommended for the first time that we should focus on finding planets like Earth. You can see it says NASA should embark on a program to realize a mission to search for biosignatures from a robust number of about 25 habitable zone planets and be a transformative facility for general astrophysics, i.e. it's a telescope, do astronomy. And so the goal of this is for the first time to actually directly image planets around a star that are down to the size of Earth and to actually get the spectra so you can see the chemical signature of what's there. And this is interesting because up until now, we have taken images of planets from the ground, but they tend to be really big planets. These are all about the size of Jupiter. These are gas giants, and they're really far away from their star, right? So if the Earth-Sun distance is 1 astronomical unit, you can see 20 astronomical units is here, and you can see that these are even further out. And you might say, well, why is there this black hole in the middle? And I'll tell you the answer in a minute. But for right now, we'll just focus on the fact that we want to find planets that, they might only be a pixel or two on our image, but they're actually much smaller and they're in the habitable zone, which means that they're really close in. It would be blocked out by this black hole. And so to take an analogy from another picture in our solar system, the Voyager spacecraft was launched almost 50 years ago, right? So it was a para spacecraft. So it's the furthest man-made object from the sun. And it came up with this picture on the right, which you've probably heard Carl Sagan talk about with pale blue dot, right? That little speck here is Earth. And on the bottom is the family portrait of the solar system. So all of the different planets are actually notated here all together, and you can see the small pixel images. So it's one of these things that I think if you go and give a talk at a school and say, look at this amazing picture of Jupiter, they would much rather see, the blow up of what we know today rather than this. But if you think about you've never actually seen that, then in the same way that that blow up of Jupiter is exciting, exoplanet astronomers are just wild about being able to get to these, Earth-like planets. And so the goal of this next telescope that I'll be launching in about 20 years, so all of you on this call now will already be like supervising the graduate students who will be working on this by the time it comes out. It's called the Habitable Worlds Observatory. And I'm part of the team that's helping to work on it. It's got a really long timeline. Also, we don't know anything about it. So this rendering has red lettering to tell you it's not going to look like this because we have a lot of decisions to make. But it's just to say that it takes a lot of time, this pink bar on the top, to think about what do we need to do to be ready for this telescope. So I mentioned that as the Exoplanet ambassador, I help design missions. And so we have a couple problems to solve. One of them is that it's really hard to see something as faint as the Earth. So that black circle you saw earlier was blocking out the starlight. I like this analogy for helping you understand sort of what's the contrast ratio, right? 10 to the 10 or 10 to the minus 10. And so we have a lot of work on both coronagraphs, which is a way of blocking starlight that's built into the telescope, as well as on star shades, which are different structures that would fly separately from the spacecraft. And they would sort of line up and block out light. We probably won't use that in the end, but if any of you are in Boston and want to see a model of it, head over to the MIT Museum, which is where I took this picture on the left. And you can actually go and see what that looks like. On the right is a picture of the James Webb Space Telescope. And I just have that there as a reminder of how hard it is to do this technology work. And I think very often in physics and science, we don't talk about what it takes to build the machines that do the science first. We just talk about the results at the back end and what we need to do. So I'll mention one other thing about HWO, and then I'll pause for questions, which is that's what we're doing on the technology side. I'm not involved in working with hardware, but there are also people like me who are thinking about, well, if we're going to have this great telescope, where do we actually point it, right? We need to figure out what the targets are. And so it turns out if you're trying to find these planets around, stars in the habitable zone, you need to look at really close by stars. And so we put together a list, and it got released earlier this year in March, that actually is what we're calling the preliminary target list for the Habitable Worlds Observatory. So these are bright stars that are nearby. They're generally like the sun, because we don't want it to have so much activity, that it causes problems, and so on and so forth. And so we can talk about the science of that later, but I think one interesting thing about my job is that I actually both bridge the science and the communication side. And so we've actually embarked on this effort to help people get excited about these stars. Because when we generally talk about exoplanets, we talk about the planets, not the stars. But it turns out there's this tool that NASA has called EYES, and I'll show you EYES for something else in a second. But EYES on Exoplanets has all of these different systems. So every planet known to date is in there, exoplanet. But we added the stars feature, which is totally new. And so you can go and follow along here on your own time. And so these are all of the stars that the Habitable Worlds Observatory is going to look at, or at least that's the plan. So I had a student who actually just finished for the summer, but because she's from New Zealand, so it's not even summer for her, but who helped write some of the descriptions of these. And what you'll see is if you come to any of these stars and you click on them, you can learn all kinds of things and see a 3D rendering, but it's kind of neat that we actually help people think about why they're interesting systems. So it's not just that, oh, this is a K-type star that's 12 light years away. It's, oh, hey, this is in Star Trek here. And when we look in the habitable zone, this is where the habitable zone is. And here are all of these different properties. And well, have we looked at this before? Yeah, actually we have. We've maybe found some planets through this method or that method. And so we actually go through the 5 different methods of how to find a planet, and have basically a literature search. So I encourage you to take a look. If you have suggestions of what you'd like to see, let me know. But it's one of these things that if you don't have the story like I do of, oh, when I was a kid, there are no exoplanets to, now there are lots of exoplanets, and everyone just says, oh, yeah, there are lots of exoplanets for the next 20 years, but they don't see thousands more being discovered all the time. How do you keep people interested in exoplanets for that long, right? What do you tell them? And so this is part of why I work with artists and do so much work to communicate the science, because part of this is just for people's curiosity, but part of it is, I need the person who's going to work on the Habitable Worlds Observatory as a graduate student, right, who is not yet born, to care about this. And what do we need to do to get there? So I have lots of different things I can talk about in outreach. I will just say as a note that I started giving talks when I was an undergrad. I went into the Cambridge public schools and did demos in classrooms with SPS, a program that I don't think still exists, but did at that time. And I've given lots of talks now, both on TV and classrooms, but also writing and different things. And I just want to say that when people look at this, they think, ooh, that looks impressive. Or when I tell people, I was at Coachella the last couple of years, on stage, they'll say, what, why? And the answer is people talk about science at Coachella. But this is just to say that everything you do sort of adds up, right? So you can see there are different things that, I gave talks for the Smithsonian because part of my grad school was jointly with the Smithsonian. My TEDx talk came from being a tutor at Mather House, which then got picked up by TED.com, which led to all of these other things. I wrote for the SAT reading exam because somebody emailed out to, the department mailing list saying they were looking for grad students who wanted to make minimum wage doing a side project. All that's just to say, if you like outreach and you think like, oh, wow, there are fancy things I can do, you are all in a position to be able to do that. So I'm going to pause for a second before I shift gears a little bit to talking about the Earth. Any questions?
I actually have a question about your core collaboration, together with the poster making artists. So I wonder how does the usual process go? Because I assume that how can I say, the actual science is really difficult to grasp all together in art. So I just wonder how the usual work process goes when you try to collaborate together with artists in order to make this kind of outreach posters.
It depends what you're trying to do. So for example, when I showed you Trappist I, here, right? We showed them the system, the orbital configuration. So they knew, okay, if I'm here and the sunlight is here, then these many things should be going away, right? On 55 Cancri E, it's got really high temperatures and pressures, right? So you have minerals condensing from the clouds. And so that's why they said like skies sparkle above a never ending ocean of lava, right? So some of this is sort of describing it in words and sharing results. Kepler 16b is an exoplanet around a binary system, right? So that's why there were 2 suns. So the general process is if you have the data and you can tell the artist about it, you do that. I'm currently working with artists on illustrations for the Habitable Worlds Observatory, and they would love for me to say, go draw this thing, but better. But we don't know what this telescope's going to look like. We don't know what it's going to discover. So it's actually really hard. And I've discovered that working with the art team, that they actually dig into the literature actually just as much as if you were starting a new research project, right? So when I was talking about coronagraphs with one of the artists last week, he knows everything about masks, which is sort of the way you block out the light, and the different patterns we use as some of our experts, just because he was trying to find something that looked aesthetically appealing, but he wanted to make sure it was appropriate, because a lot of people worry that when they work with NASA, if it's not realistic, then you can't use it. So it's a really interesting process. I will say a lot of these posters, like this one, are done by my friend Joby, where a lot of our artists used to work at Disney, for example, because what do you do after you design things for Disney? Well, you come and you work for NASA and you design new spacecraft, which is kind of cool.
Wow, that's really cool. Thank you so much.
Welcome. Any other questions before I go on from exoplanets to the Earth? You can't tell if that's a hand or if that's a movement. Oh. All right. I'm going to move on for now, but we can always come back and pause. And I realize I'm talking a little slowly, so I will try and pick this up a little bit. But this is not an art campaign that I did, but this is to say art does connect in different ways for people. And as we're talking about climate change, right, it's one of these things that has huge impacts. So if you think about what NASA can do, you don't generally think of NASA as the first place to go for climate change, but I actually came to JPL a few years ago to help build out what we do in climate change. And that's because we have all of the satellite data, right? We can tell it's been really hot this past week. And all this data, right, this is from eyes, but eyes on the Earth. You can see carbon monoxide from the fires in Canada now, over the Atlantic, not in the cities. All of this you can go, this is soil moisture, so you can see drought in California and Brazil and Africa. All of these things that it's kind of neat that you have data for the most remote regions, so you can help with equity issues, right? You don't need to have sensors everywhere, but also things like sea level rise. Without satellites, we actually don't have great coverage, right? So it turns out that in the last 30 years or so, we've had this continuous record of satellites monitoring sea level. So you can see the different ones there, and you can see the general trends. But the thing that I think is really interesting is how much we didn't know before we had that satellite data. Because you can look outside at the coast, right, with a tide gauge and measure where the water is. But you actually can't tell a lot about the processes over time unless you have these continuous observations. And especially, there are some cool tricks we can play. So one of my favorite spacecraft is called GRACE, or GRACE Follow-On. There are 2 different sets. So this is a picture of one of them, where it's 2 satellites. And in the same way that LIGO does interferometry, right, with a laser, there's one that does this with microwave, another one that does it with a laser, but basically it's checking the distance between these 2 satellites at all time. And as they travel over the Earth, the mass of what it's traveling over, right, the gravity varies. And so that variation in gravity affects the distance between the 2 spacecraft. And so because of that, you can then actually get a sense of the mass underneath you. And so this is how you can get these observations on the left of the ice sheets melting, right, in Antarctica and Greenland. So that's how you have these videos. And so you can see on the bottom, and it's showing up on the top, all the areas where the ice is just being lost. And so it turns out that GRACE and now GRACE Follow-On are the way that we know that sea level is rising in part from glaciers and ice sheets melting. Like, to me, that just seemed really obvious, but it's actually only in the past couple of decades that we've come to that understanding, right? And so it turns out that when you think about climate change, heating, right, and thermal expansion only accounts for about a third of sea level rise. And the other third is from glaciers melting, and another third is the ice sheets, where the ice sheets are just Antarctica and Greenland. So this is a map that was in a paper in Nature, but also is used in the US government's intelligence reports to understand what's happening with freshwater. So you see that Greenland and Antarctica are having a bad day, but there are all these other regions of the world where wars are going to be fought, right, over decreasing water. And it's one of these things that you're not drilling down to see what's there. You're using spacecraft and this, unique record of satellite data to see what's happening. And so just for comparison, by the way, all of these red dots are where we have tide gauges, right? These coastal dots. If you're curious what a tide gauge is, this is a picture of one that I saw 2 years ago. It's, a big column that you have down into the coast, right? And you can see sort of how the buoy raises or lowers. That's by the Golden Gate Bridge. So this is from a paper. Well, there are two versions of it. This one's published. There's another one that's currently under review, where we're trying to figure out how do you actually use the satellite data if you are someone who has to deal with it. Because the problem is we know the climate is changing, but we don't know what to do in the future and what we need to do. And if you're going to tell a city that they have to move, you need a lot of time, right? But if you're going to just add some sand, that's pretty quick. And the range of uncertainty is a lot. And you need to figure out how much money you need to spend to deal with it on this time. So there is this idea that came about a few years ago. People use it in different ways in climate change, but the idea is called an adaptation pathway. So this looks like a metro map, right? So time is on the x-axis, but we don't think about it in terms of time. We think about it in terms of conditions. So you can think about it as sea level rise. So these are a bunch of different things you can do. So on the left is the sort of general example, so action A to D. And so if you're here and the sea level is rising, you have to get to this point and you're like, what do I do? Okay, maybe I'll build a road. So you go up to action B. So you build your road somewhere else, but then the sea level keeps rising and it doesn't work anymore. So every time you come to a point, you have to decide, am I going to keep going with it or do I have to change path? So on the right is an example from a technical report that was written by the US government from different agencies for Falmouth, Massachusetts. And you can see things about bridge construction, seawalls, different things. And you can see sea level rise is the x-axis, but then these two different parts of year are very different, right? In one case, 5 feet of sea level rise is in 2100. In another, it's maybe 2075. And so thinking about these examples and what triggers you to move from one to the other, on the left here are different examples of what you actually watch to decide to trigger these changes. And you can see that the city of Santa Cruz out in California has things like, are there any erosion damages to the state parking lot? Which that makes sense, but maybe you can do better with satellites. And so what we did was to try and look at where people use these adaptation pathways worldwide. The answer is not a lot of places. And you notice that most of these are highly developed countries. And what data could we take to help them do better? So this is ongoing work, but we put everything into sort of 4 buckets. One of them is instead of making all of your plans based on how high the sea level will be in 2050, maybe you can make plans based on what the current sea level, is, and make your plans dependent on constantly adapting to the current values, right? Maybe instead of using what the total sea level is coming from UN reports or others, you can look at your different regions because you can see that there's huge variations in the amount of sea level rise across different parts of the United States even. And it's even more interesting that maybe you can use Antarctica melting to help you decide what should happen in your planning, right? That figure I showed you before. And that's because if you're in Mississippi, most of your sea level rise is coming from actually the ground subsiding and shrinking, right? Whereas in Maine, you have a lot more relatively coming from Antarctica melting, right? And in American Samoa, all of these things are different, right? And actually, I guess I should say, for the Atlantic, North Atlantic, the heating of the ocean and how the currents move around affects this a lot. But, for someone in the city of Santa Cruz, mayor's office to think about Antarctica melting is not a thing people have done before. And so right now we're working on helping people understand how they can use this data and finding ways to track these different scenarios so that they can make better decisions. Because if we look at an example from American Samoa, you can see that they had an earthquake, right? 2009, it's like Tonga. And so if you look at the GPS, you'll see that the land went down, right? So that's the land displacement, so vertical land motion. And you'll see that all of the trajectories of what should have happened are totally wrong compared to sea level rise. And that's because if your ground goes down, then the ocean seems higher relatively, right? And so you have to combine all kinds of different things together. And so helping people make observations, whether it's a visible image, right, with a drone or a spacecraft of the size of your beach and flooding, to something else. This is all something new that we're working on. I didn't realize that in a lot of places we add sand to beaches and then it gets eroded away, and we just keep adding it as a way to deal with sea level rise. And so using satellites to do that is a thing we do. Okay, so the last couple of minutes, I'm just going to mention what it's like to work with the government. But before we do, does anybody want to ask me anything about sea level rise, actually? And if you prefer to hold your questions, that's fine. All right, I'm going to carry on then. It's just a couple of slides, which is, you can see that I sort of blend a lot of different things together: the astronomy, the communication, you know, helping people in government. And part of this is when I was in grad school and when I was in college, I wanted to help people, and I wasn't sure that being a physicist did much of that, because it's not a doctor saving someone's life directly. It's, you know, a little bit more abstract. So I went and worked for the government. I was what was called a White House Fellow at the end of grad school, which is a little unusual. And when I was chosen as a White House Fellow, so about 16 were in my class, you get to work for any department of the US government. And I said, don't send me to NASA, don't send me somewhere where I already know what it's like. I want to do something different, and I want to do something that matters. And so in grad school, I did a lot of farming and I did a lot of work on waste. And so I went to the agriculture department. And when I was there, I helped the economists deal with climate change, which ended up being my focus, and thinking about how do we use new sources of data. And one thing they asked me is, Anjali, would you like to go to estimator school? And I said, what's that? And they said, it'll help you estimate the crop yield of, you know, an area by looking at ears of corn. So what it is the way we do our agricultural census in the US at some level. And, you know, if you ever watch a movie called Trading Places, with Eddie Murphy in it, you'll see that they talk about frozen concentrated orange juice. But anyway, there's all of these stock market things related to the agricultural forecast. And part of it is that every month the USDA releases what they think the productivity is, but they're not going to measure every acre of corn in the country. So what they're doing is they're calling some people on the phone and asking some questions, and they're sending some people into fields where you walk into the field, you go 6 feet to the right, 10 feet to the left, pick up the second ear of corn that you see and count the kernels on it, right? So these are figures from like estimator school, where they then say, okay, well, because how close you plant the corn together matters. All kinds of different things I learned that were fascinating. But this is how we actually make these estimations. It hasn't changed since the era of Lincoln. They don't use satellites. And so that's one of the things we worked on with them. So that's just to say that there's a lot that happens in government that's just sort of different than what you expect. And so I started in 2016 and I worked there also in 2017. And I started in the agriculture department and I worked on things like, how do you do a better job of estimating crops? And how do you prepare for pandemics, which at the time we were only talking about like bird flu. And then when it changed administrations, I said, actually, you know what? I think I can come and help with science. But this was my White House Fellows class, a lot of lovely people here. This is Sharice Davids, who is now one of the first Native American women in Congress. But she's a lawyer by training, all kinds of cool people. And you might say, well, what does a physicist, astronomer do in the White House? And the answer is a lot of different things, right? So I mentioned working on climate change. So I was the acting in the role of the executive director of the National Science and Technology Council, which is the way that the US government organizes everything that it's putting out from the executive branch. And so this was a report, this was the first one about anything related to climate change of the Trump administration that we released. So it was about algae in the Great Lakes and what that meant. Helped write policies around drones and AI that, you know, allowed for testing, near airports. So on the left is from an event we had with the president in honor of that. You can see Vice President Pence had a tweet with me in it over here, and then president of MIT, all kinds of things of how do you protect the Apollo landing sites on the moon, a bunch of different things. And so the answer is that I'm a generalist, right? So I do work in astronomy, I do work in exoplanets, but I'm also really fascinated by a lot of these things. And I think the thing that's got me through and what I wanted to end on is just that being a good communicator matters everywhere, in your research papers, in outreach, everywhere. And on the top right is a picture of a meteorite that's in the White House. You can look at the caption on the left. It's not great. It's not the oldest known natural object, but that's okay. But I used to have to explain that all of the time. And it was kind of interesting. And it's just to think about who you're talking to and why do you want to tell the story, right? How does this connect to everything? These are some slides from some lectures I give at UC Riverside about science storytelling. So I will stop there and answer any questions and we can dive into things further. But hopefully this gives you a glimpse of what, a non-traditional career in physics can look like.
Wow, thank you so much, Dr. Tripathi, for the amazing talk. Now we are moving on to the Q&A session. So please, as Jennifer explained, and in the beginning of today's event, please raise your hand in the Zoom participant sidebar and we'll call on you. Or you can privately send a message to us and then we'll call. We'll also take questions for that. So please raise your hand if you have any questions. While people are thinking about the question, I actually have one, a question in kind of general. So I believe you have very wide, how can I say, very wide research interest in the I think the exoplanet and the more climate change related issues are a bit very different type of the projects, I would say. So I wonder how whether those kind of motivation for each of the project are entangled to each other, or I just wonder your internal kind of thought process on the motivation and passion of the both of the projects that you are working on.
Yeah, so I do a lot of very different things. And I would say that part of this, and sort of what I was alluding to earlier when I was showing all of the different ways I did outreach, is if you're interested in something, just sort of go after it. And I say this because one of the things that kept me busiest and probably sane during COVID was that I actually became the head of vaccine data for the Los Angeles County Department of Public Health. And you might say, right, some of you are going, what? Yeah, no, I have no public health degrees. I mean, here, I can grab this from my desk. Okay, so I have this thing, right, from the county public health department, because I became the innovator of the year, which is very weird to get a trophy as an adult. It's like what you get in elementary school. But because my mom is from Taiwan, right? And early on in COVID, she didn't think she needed to stay at home because in Taiwan, everybody goes out and about during COVID, just wear a mask, it's fine. And so I took the department press releases and I started plotting the data on a map of LA. And I actually just put it up on my MIT web space. And I wrote to the public health department in the contact us button at the bottom of the page and said, hey, if you ever need any help, I used to work for the White House and I know something about data, let me know. And that was in April of 2020. And I helped them since then. And so by December of 2021, when they said, okay, we don't know how to deal with vaccination data for this many people, Anjali, it's your problem. I had to figure out how do I deal with everyone's private health records and all of these things. And if you had at any point prior to 2021 told me that I would be the person in charge of where we were deciding to vaccinate people for Los Angeles, it's the most populous county in America, I would have told you that you were crazy. But the fact that I did, is just an example of, if you want to do something, ask, right? And then do good research. And so that's why I said I'm a generalist and it works for me. But I just like working on problems that I find interesting. So at the moment, I work on sea level rise. I'm working on 2 exoplanet missions. I'm working on, I don't know, a couple of different things. I'll be in DC next week filming a documentary and meeting with the New Zealand in British governments, right? But that's just to say that it's just because they're things that I find interesting. I will also say, as a side plug, you know, I also do the MIT Mystery Hunt. Do any of you know what that is? Okay. So MIT has a lot of weird traditions, I know. So I'll just put this one up real quick. This is a puzzle. You know, you can all Google it and see it. But it turns out that this is a cute little word search where, I don't know, do I have, no, I don't have the answer. It turns out that this is the sun, and this is actually Mercury with an extra letter H. And then around it, it's like, there should be Venus, yeah, Vienna, right? And so on and so forth. It's a bunch of puzzles where there are no instructions. This is something that happens every January. I run a team called I'm Not a Planet Either. If any of you would like to join, talk to me afterwards, always a spot. But it's just to say there are lots of really random things out there that you don't know about on day one. And so part of why I started the talk with all of the different things that I never knew about up front is just because you don't know until you try. So, you know, you might as well. Okay, that was very long, and I see a couple of people have questions. So I'll let you all go on to that.
Thank you so much. And maybe we can go from Hillary. Oh, sorry, 1 second. Oh, sorry. Yes, please.
Okay, does that work? Okay, I'm unmuted now. First of all, I want to thank you for this very insightful talk. This is very inspirational, and I would personally say I'm a generalist myself, so to hear from someone with this kind of experience is very inspiring. And I have a couple of questions. First is, considering your background from MIT doing research and then doing policy, how has your relationship with physics evolved over the course of your career? How do you think about physics, and how do you use physics in your life? How do you conceptualize it? And
yeah, go ahead. Oh, did you want to say your other question, Hillary? You went back on mute. I don't know if I need to unmute you.
Oh, I think, yeah. The other question is, how do you decide to take an opportunity when it comes up? Because sometimes a common advice I hear is that you get to make more of an impact if you have more depth. But if you dabble on many different things, how do you, you know, make a bigger impact in that kind of field? And you've worked in different things, so.
Those are both good questions. Okay, so the first question is, what's my relationship like with physics? So as I sort of alluded to, I was not the top student in my year in physics at MIT. I have to say, I found studying physics at MIT hard. Like, I don't think there's another way to phrase that. And so much so that I felt like I was not cut out for it. Because I never felt like I had the understanding, or, you know, I remember all of my professors would say, oh, like, I wake up in the morning thinking about a physics problem. And like, I almost never wake up in the morning and think about a physics problem. Does that make me a failed physicist? Maybe. But it's one of these things that a lot of the sort of general principles that you learn, right, you know, come back and get applied all over the place. So for example, talking about COVID, right? One of the things we were trying to do was talk about, you know, aerosols falling on the floor, right? And what are the timescales, right? Back when everyone was like spraying Lysol on packages at their doorstep or whatever, and hand washing. I've never taken a course on, you know, molecule, you know, in different viral, you know, I can't even phrase the question properly, right? Because I don't know anything about it. But having an understanding of like fluid dynamics and things like that, which I have studied, like there's always something that's applicable. And so I'd say I'm really grateful for my physics background, both in it being really hard, so having to know what to do when you don't know what to do, as well as trying to figure out the new thing. Like most of the faculty who are older, who are in exoplanets, didn't get their start in exoplanets, right? Because that didn't exist when they were graduate students. And so they've had to sort of figure it out along the way. And so when I introduce myself to people, I generally talk about being an astrophysicist or an astronomer, just because it's a point of reference for things. And the fact that I do science communication or policy, those are different applications of it. But I think that same skill of both analyzing a problem and communicating it is really translatable. So that's kind of general, but hopefully that starts to answer parts of your question. And then the second question you asked of how do you decide what to work on and when to say yes or no, and specializing versus being broad. So I will say that the conventional wisdom is like for those reports I showed you, for example, about, the Apollo landing site being protected or harmful algal blooms, there are members of the National Academy who have contributed to reports like that. You get to be on the National Academy by being a distinguished academic in your field, right? I am not a distinguished academic in my field. I have papers, I publish sometimes. Most of what I publish these days, though, you will never see my name on because it's got, NASA or the government or something on it. And so it's one of these things that is a route that's definitely very valid. And if you enjoy it, that's great. For me, I really didn't enjoy being that focused because I really liked thinking about other things. Like I have, I don't know who advertises these things, but for example, if any of you are familiar with Freeman Dyson, right, who was a physicist at the Institute for Advanced Study, he was a part of this group called the Jasons. And they are physicists who consult for the government every summer. And, he would spend his summers thinking about all kinds of things. Like when I was at the USDA, a bunch of astronomers came and talked about satellite observations because it was, a thing related to work they had done elsewhere. So I would say that there are all kinds of opportunities, even if you go down that focused path. I would say if you go down a broad path, though, to make sure you build enough depth in each area so that you can speak intelligently about it. Like part of my work in sea level rise is it's not just me, it's me and a bunch of sea level scientists who have been doing this for years, so I can sort of get up to speed, right? With the COVID work, there were epidemiologists who work with me. So having, basically a partnership with others, I think can be really helpful for gaining depth. But when to say yes or no, I think the hardest thing also is to be able to say no, because one step is how do you make the opportunities appear? But then the second is you have this FOMO of if I say no, what happens next? And I think you have to make these decisions sort of on a one-off basis of what am I prioritizing today and what is that going to get me in the future that I can then make this look like the adaptation pathway at that next step, iterate. Okay, I'm sorry I'm going on for too long, but Nino next.
Hello. First of all, thank you so much for the fascinating talk. I also just wanted to let you know I've been very excited about exoplanets since high school, and NASA's Exoplanet outreach has definitely been a big reason for that. So thank you for everything. And I had a specific question about the Trappist I system. So I know you meant it's very exciting how there's so many habitable rocky planets in one system. And I remember reading worries about how the host star is has high stellar activity and the planets could be tidally locked and stuff like that. And I was wondering what your predictions are for the existence of atmospheres around those planets and what we expect to find out in the future from James Webb maybe. Mm-hmm.
Yeah, so it's a good question of what do we do with all of these active stars, right? Because we tend to look around M dwarfs, right? These smaller stars, because the habitable zone is closer in, so a period is less long, so you can, in your observations, get a sense of the planet. But a smaller, a red dwarf is more active. So, for Trappist I, I'm not an expert, so that's the first thing I will say. They have already, there was a Nature paper, again, there are a couple, there's one from March, and then again, there's one, it's sometime last month, because we were just discussing it in a meeting last week, that have shown minimal atmospheres on the planets that are closer in, which is not surprising, right? Because they're closer in. I mean, yes, they're bigger, but there's no reason to believe that that has to necessitate a big atmosphere. So all that is to say that I don't think having a ton of stellar activity in general is great for your planet, but it also doesn't mean that it's game over. If you look at our HWO target list, if you scroll through that page, you'll see there were maybe, I don't know, 4 M dwarfs on it. And part of that is because they're actually nearby that we can see. And so given the statistics on everything, it seems likely that you'll have planets that aren't totally, I don't know, washed out with stellar activity. I feel like you asked another part of your question, and I don't remember what it is. So if you can help me remember, that would be great.
Yeah, it was kind of just talking about the tidally locked aspect. Yeah.
Yeah. So tidal locking is a weird thing, right? I mean, in the solar system, and I guess, right, there's different kinds of tidal locking, right? Because you can have, for example, the moon and the Earth are sort of almost perfectly tidally locked, but not quite. And then you have things that are in orbits, right, where it's, to do with resonances. So if you look at something like the moon Io, which has all kinds of other interesting phenomena like volcanoes. But when you think about that and the implications for life, there's all kinds of challenges because the heat has to be redistributed around it in some way if you're close into the star, right? And how the system can behave, right? Like, do you have this sort of magma lava world, or do you have something that's all gas? Like for the systems that I modeled, right, the hot Jupiters, those are all tidally, right? And so you had just the same size always getting irradiated. And so you had to redistribute the heat and the gas. But of course, solids can't do that as well. And so how that's going to play out is sort of an open question, I would say, because we don't have enough examples of what that looks like. And from what we've seen, it seems like you could have quite a diversity of options. So I do not have a good answer for you, but it is definitely a concern. But I would say that these questions of sort of the geologic activity of a planet are sort of second level, right? Like first is like, is the planet there? Okay, does it have an atmosphere? Does it have a rocky surface, right? Like what's its bulk density? And then after that, we can go into what are the thermal processes and like the volcanoes and whatnot. So I don't know if that was unsatisfying, but in the spirit of not being an expert on these things, I am owning up to my lack of deep knowledge.
That makes a lot of sense. Thank you.
You're welcome. And I'm sorry I've gone so over. I tend to talk too much.
I have one more short question, if yes.
Yeah, go for it, Tom.
So what is one like scientific explanation that you are the most proud of?
Oh, I don't know about the most proud of, but I'll show you one that I'm proud of that I've been using a lot lately. So I went to the American Astronomical Society meeting last month. And that was one of those pictures I showed you at the beginning. You saw a picture of me holding these two jars. So this jar, and then if I can not drop it and have to clean up a ton, and this jar. Okay. Does anybody want to guess in the chat what each of these beads represents? It's not that hard to guess, but I'll let you guess in the chat, right? We've got two jars. Okay, number of test objects of interest. Okay, not quite, but and like, because you might think like, well, why are there two jars, right? And this is the legend, by the way, the string. Okay, any other guesses before I tell you? I'm really glad I didn't make this part of my talk. I was going to make all of you guess what was going on in here earlier, and I saved all of you. Okay. So small jar is potentially habitable planets. Okay, so all of you are in the right ballpark, that these are related to exoplanets because that's part of my job. So each round bead, right? So in this one, they're all clear, is a gas giant planet, right? The stars are their host stars. There should be a gold one. Yeah, there's a gold one. The gold ones are terrestrial sized. The blue ones, here, let's look at the legend, shall we? Okay, host star, gas giant, Neptune sized or mini Neptune, super Earth, and terrestrial sized planets. So just like that figure I showed you with the different planet sizes, these are the different planet sizes. And each jar represents the number and type of exoplanets in a given year. So this is the year 2003, and this is the year 2015, right? I went to college in between the two of them. And if we had 2023, it would be about 3 times the size of this. So this was a game that I had at our booth for people to guess the number of, like jelly beans in a jar, which, by the way, I used to teach science and cooking when I was at Harvard as an example of like all the random things I do. And I remember the main thing I learned from that class is how to win jelly bean guessing competitions. Like I crushed one at Harvard's health services and helped my physical therapist win, I think, a Fitbit. But anyway, so I have, of course, a Python notebook that calculates the size of the jar and the beads and everything that I need that'll do all of this for me. But I was sort of pleased at having a way for people to visualize, right, the number of exoplanets and the differences, because here you can see it's mostly clear beads, right? The stars are colorful. Whereas here you can see lots of blue beads and green beads. But you notice there are just a handful of gold beads, right? I actually had to put them on the top because you wouldn't see them. And so getting a sense of if the school of a telescope in 20 years is only going to get me 25 gold beads, you know, why do I need to spend so much money and time to get there? The answer is it's really hard. So I just like this because it's a fun thing that anybody, like a graduate student, a teacher, can reproduce, and they can talk about the different things. You could color the beads by, you know, how the planet was detected, but it's a simple explanation. And the other one I'll share with you was just around that picture of the meteorite that I showed you from the White House, because I didn't know that was in our conference room until one day a member of Vice President Pence's staff came up to me and said, "Hey, I hear the oldest object in the universe is in this building. Can you show it to me?" I can show you the meteorite. Yeah. And so I took him to see the meteorite, which again, you saw that picture. It's just a black rock, right, with white dots. It's not that interesting looking. It's not like one of these beautiful iron meteorites with etching patterns from melt. And I explained to him, I said, this meteorite, you know, all of those white dots are the same material that went into forming the Earth, right, and forming the solar system. So it's like if you were in your kitchen and you were baking a cake, and you're like me, you're a little messy, so flour gets all over the counter. You bake the cake, it goes in the oven, it comes out, you eat it, it's gone, right? So like the cake is like the planets, but the flour left over that gets fossilized by other things, that's those white dots in the meteorite. And so I said, like, you can think of this as the material that went into forming the solar system. He really liked it. He really liked cake. And so it's something that he then started sending me all of the vice president's guests to come and learn about chondritic meteorites from the astronomer on the 4th floor. So those are my 2 stories.
Wow, thank you so much for sharing amazing story. And if there's no more question, yes, maybe Kwan can do the closing remark, and then we can wrap up for today.
So yeah, thank you. We are at the end of our time, and for those of us who are joining us for the first time today, please sign up to our Chilloquium mailing list through the link that Michelle just posted in the chat. And we send out a weekly email about the upcoming Chilloquium talk and a reminder on the day of event through this list. So if you want to stay up to date on what talks are coming up, please join the list. So thank you so much again, Dr. Tripathi, for a wonderful talk today, and we will see everyone next week on Professor Irina Kim's Chilloquium talk. So thank you and goodbye.
Thank you so much for having me.
Thank you so much.